Okay, so here we have FMA problem 15 from the 2013 exam, and it looks quite innocent right here, and all it asks, there's a rod on a pivot right here, some length, and there's water, and we're asked what percent of the rod is above the water, and we're given the fact that the density of the rod over is 5/9 the density of the water. So the wrong way to solve this, I would say, is to, well, first thing I thought of when I saw it was to specific gravity. 5/9 means that by specific gravity, 5/9 of the rod is under the water. So that would mean that the answer is 4/9, which turns out to not be the right answer because the fact that it's on a pivot is important. You need to make sure that you're aware of this because it's not like it's free floating on water. Then it would be 4/9 of it. But this time, like, the gravity is influencing it, and then the water is also influencing on part of it. So this problem turns out to be a much bigger beast than that. So I guess the first thing we should do is to find out what we're looking for. Well, if we define the amount that's above water is to be L, and the length of the entire rod to be uppercase L, then we're trying to find L over L. So there's a pivot. That's one thing that I noticed. And when I see a pivot, I think it's going to be a torque problem. If we don't want the rod to move, we need to think about when it's in equilibrium. So what forces are acting on it? Well, first, gravity is acting down. There's some torque from gravity. And then somewhere on the rod, there's a torque of the buoyant force acting on the rod. To solve that, well, this is an FMA problem, so I'd expect, well, since it's not in motion, the torque of the buoyant force equals the torque of gravity. Okay, so now we have to figure out what each of those are. So now that we know that the torque from the buoyant force and the torque from the gravitational force are equal, now we have to just find out what they are. Now let's stick with this simpler one for now. Torque of gravity. Well, we know that torque acts on the middle of the object, so the distance that this acts on is L over 2. That's the distance for the torque, and then the amount that it's doing. Well, we don't know the mass of the rod, but we do kind of know how much of the rod, or like the length of the rod that's under, and how dense that length is. So if we take the density of the rod times the amount that's having its force on, which is the entire rod, so this is L, and we multiply that by G. That's the torque of gravity. Now, for the torque of buoyant force, this one's a lot harder, but you should know now that torque, or the buoyant force, acts in the center of the amount that's submerged. I think that's kind of easy to figure out. You can probably derive that by knowing how much the force is acting on each part should in the middle. By symmetry, you should be able to just assume that it's coming from that mass. So how far is this from the pivot over here? Well, let's find the length of this. Well, since this perfectly splits up the remainder of the rod, you have L minus L over 2, and then we have to add on the L. Okay, so we found that the distance from where the rod begins to be submerged is L minus L over 2, and then we add the L. The distance will be L plus L over 2, and then the buoyant force is equal to the weight of the fluid displaced. Now to find that, we take how much of the rod is being submerged, which is L minus L, multiply that by the density of water, because that's the fluid, and then the weight means we have to add G, because this is just theoretically the mass of it. So then we end up with the torque of the buoyant force is equal to the weight of the fluid times the distance away. So let's write that L plus little l over 2 times L minus L times the density of the water times G. Now we return back to here, going the second part of solving this, which is setting these equal to each other. So we have L over 2 times density of the rod times L times g equals L plus little l over 2 times L minus little l times density of water times gravity. Now, time to simplify it. We get rid of g's. And then let's get something that we know. If we divide PW by both sides, then we have PR over PW. And now we can also get rid of, there's a divided by 2 on both sides, so get rid of that. So this is messy, so I'll fix it up now. What I notice is that this is a difference of squares, so be big L squared minus little l squared. Well, remember what we're trying to find is L over L, or big L, little l over big L. So at this point, I would think, I forgot the R here. Okay, so I would think we should divide both sides by big L, so we just get the known on this side. So PR over PW equals 1 minus L over L squared, little l squared over big L squared. Well, that's just what we're trying to find squared. So I would fill this in now. So 5/9 equals 1 minus, and instead of saying L over L, we'll just say A for like the answer. So now we get, if we solve for A now, well, we have A equals 2/3. And I remember the problem asked for that, like the closest answer, and one of the options is 0.67. That turns out to be the correct answer. And we're done.